Okay, my clock is low now, so I guess we just get started, and we'll continue what we talked about last time. So a little bit review that we are looking at count warping. So it can be like lots of applications, for example, like for image stitching and so on. So we mentioned last time that like we need something known as this homogeneous coordinate. So basically, like you have a, if you think of a 2D image and you look at the coordinate of each of the pixel, so you have x and y values there. So instead of like just x and y, we talk about we are going to append a 1 there. So let me just, I hate to write here, so let's see if I can. Why my signal is hiding at the back? Now where's my signal now? Capture. I don't know whether if I. Okay, this pretty weird. I'm not able to. I guess that's the only way I can do it. Oh, okay. Yeah, okay, that's fine now. So okay. Okay. Let's move things around a little bit. Okay, that's better. So say we have this x and y coordinate there. We said like we will append a 1 there. So and if we're going to transform like this, so therefore this new homogeneous coordinate, like of course like we have, in general it doesn't necessarily to be 1. If you remember like that maybe this is equal to w there, then like how you interpret that, like if x, y, w, the actual Euclidean coordinate that you see on the screen will be x over w and y over w. And so now if we want to map like the original coordinate like in the image to a new coordinate there, so we say like in order to like basically include also the translation, so we introduce, that's how we introduce this like homogeneous coordinate, and then all the transform that we are interested in can be like just think of it as a matrix multiplication. So we have a basically have a new coordinate like x pi, y pi, and maybe w, and it's equal to this multiplied by a matrix M, let's say, and last time we said okay, if the whole thing is like arbitrary, that the transform is known as a homography. So if we have like the last row there is 0, 0, 1, that is like that will be restricted to the affine transform there. So in that case will be affine. And we talk about how to fit the model. So say if we have some known kind of like original coordinates, some known like final coordinates there. Let's say I have like x, y, x1, y1, and map to like x. Maybe I write the other way. X1, y1 map to, let's say, x pi 1, y pi 1, and x2, y2 map to y x pi 2, y pi 2, and so on and so forth. Then we can just build a system of equations. So last time we take an example like doing the affine transform. So if we also in the notes, actually in the slides, we illustrate like how to do it just for translation. So if it's just for translation, then the transform will be restricted to something like 1, 1, 0, 0, 1, and translation of x, translation of y, something like that. So these are basically the unknown parameter we want to fit, right? And so in that case, let's say, just take this example, like simple example again. So I can, for this first coordinates here, first pair of coordinates here, I can form two equations, basically like x1 pi is equal to x1 plus tx, right? And y1 pi is equal to y1 plus tx. And I'm also like, let's say, consider this pair also. So I have like another equation, x2 pi is equal to x2 plus tx, and y2 pi is equal to y2 plus t. I'm sorry, like I put tx everywhere. This is ty, of course, plus ty here. Then again, like these are the unknown, we can just put them together. So I can rewrite this as a tx, ty. Let's see, how do I do that? Like this is equal to, let's see, the first equation basically is like, I have x1 pi, tx is just equal to 1, right? I need to put a, let's see, yeah, that's fine. Okay, that's fine. So I can move this to the other side. Basically, I just have like 1, 0 is equal to x1, x1 pi minus x1, right? The first equation is like, I can write as a tx is basically just equal to x1 pi minus x1, right? So, and then like the second equation, let's say I can now write as like CO1 is equal to, that's basically like ty is equal to y1 pi minus y1, right? And similarly, I have like two more equations there, like 1, 1, and this is like x2 pi minus x2, y2 pi minus y2. And then we say like we have this kind of system of equations. So in general, like we have kind of like many, I mean, like that's not no was to say like a perfect solution for this one. Like I mean, perfectly satisfy this set of equations, right? So instead, like we should consider the least square solution. That if I call this a, this is called x, this is y, something like that. If we try to minimize, like let's say ax minus y, something like this is like the second norm of that. So ax minus y basically is a vector. So this is just or like I can write as a ax minus y transpose times ax minus y. And then last time we said if we just find the minimum there, so that basically we take the derivative like with respect to x, then we will get solution something like a is just equal to x is equal to y a transpose like a transpose a inverse, something like that. So this is like basically known as a pseudo inverse of. So that's like and for also like if you want to fit for, let's say affine transform. Let's say we look at affine transform. The solution is the same. Like I mean the approach is the same. We can just write down also the set of equations. Then we try to kind of like find solve for those parameters there. So maybe if you remember like what we did last time. But by the way, the slides here didn't have that. So let's ignore that one. So we did that last time. So but now let's look at like how about if I want to fit the homography. It will be a little bit different. So therefore I want to go through that as well. So think of it, I have a homography now, so the entire matrix is variables. So okay, first of all, like as I can, if you remember, even though I have 9 parameters there, if I have a homography, I have 9 parameters there, like all of them are kind of arbitrary, but I only have 8 degrees of freedoms here because like really the output here is I mean the scaling doesn't matter. I can scale that homogeneous coordinate multiplied by any arbitrary scaling parameters, and it will still refer to actual the same coordinates here. So therefore, that I actually have 1 less degree of freedom. So let's look at the first potential approach. What I can do, like maybe I just write A, B, C, D, F, G, H, 1, let's say. So I have 1 less coordinate, right? So maybe I can write like this. So, but, and then I want to have, let's say, this multiplied by this is equal to this one. But this is not a good approach. So we're kind of forcing, like the last one here, that we need to have, if you look at the first 2 equations, if you look at the last equation here, we basically need to have like xg plus, or like x1g hy1 plus 1 is equal to 1. And also like, maybe if I have another coordinate x2g plus hy2 is equal to something like that. So we are putting an arbitrary, so if basically we cannot do that. What I'm saying, like if I force this equal to 1, then I basically force arbitrary constraint here to this input coordinate, right, as you can see here. So what should I do? I should go back to the original kind of like, I mean more general definition here. So I can force this one to be 1. So in general, let's say this is W here. So, and then just erase something. Then I will have this is equal to of course I can have like equation that is now this is equal to W. Then each time I have 3 equations now. So I can have this is equal to W, and then I can have like dx1 plus ey1 plus f is equal to, now this is another problem here. So if we say this is equal to y1 pi here, and let's say if I write down a x1 plus b y1 plus c is equal to x1 pi here. So this is not mapping the real coordinates there, right? So what I'm saying, like here the actual coordinate is this one. So this is like, okay, this is my first intuition of what I'm supposed to do, but it's not a right intuition. What I should do is like, okay, I want to map directly to this guy. So you should think of this is actually the x1 pi and y1 pi there is equal to x over w and y over w. I mean, or like whatever. So therefore, like I really should have like x1 pi is equal to g ax1 plus by1 plus c. Now m over this gx1 plus hy1 plus 1, say. Okay. And y2 pi as well, I can write this is equal to so y1 pi here is equal to dx1 plus ey1 plus f for gx1 plus hy1 plus 1. Okay. So it gets quite a bit, looks a bit complicated here. And so first of all, like, I should be careful, like what are the unknown variables here. So the unknown well, actually I want to say like this actually I want to take it back a little bit. Like I want to make this as I instead of 1 here. So what I mean, like I'm not trying to think of like why I need to do it. Like basically, like if I pick a 1 here, I may be able to solve this A, B, C, D, E, F, G, H here, but the constraint there is not so of course the difference here is like if I put a 1 here at the beginning, or I am kind of forcing like one of these guys equal to 1, and then the rest can be arbitrary. It turns out it's not a oh, actually I shouldn't say that, like because I didn't try that out. So but now it came yeah, okay, I will put an I here, so I hope everyone is happy about that. So I let this also a variable as well. So just loosen the problem a little bit. So if I let this force to 1 here, so it basically will force all the variables here, like to, I mean, force them to be normalized in the sense like this 1 is like equal to 1. But it may not be able to solve the problem. So okay, anyway, so I force this to I allow this to be I now, also a variable. So now then I can move everything to the other side. So let me move everything to the other side. So I have like x1. As I mentioned, I need to be careful. These are the variables. So basically, maybe I just write this like the variable are. I have quite a lot of variables here. So. Erase that. It's okay. I have a variable A, B, C, D, E, F, G, H, I, right? Now I have the first equation is something like let's see. I have a. Let's see. Sorry, A should be x1 times A right here, and then. Maybe I just write one more step. So I have this is equal to A x1, or like maybe I write x1a plus y1b plus c, and minus x1 pi g minus y1 x1 pi h minus x1 pi I, right? And is equal to 0. So then I put everything here like x1, and this is y1, this is 1 here, I have 3 zeros here, and then I have like x1 pi, y1 x1 pi, and I have minus sign here, and minus x1 pi. Right. And then the second equation, like, kind of similar. This one should be equal to, if I move everything to the other side, it's like x1d plus y1e plus f minus x1 y1 pi g minus y1 pi h minus iy like y1 pi I is equal to 0, right? So again, this will be like 3 0 first, and then I have like this is x1, y1, and 1, and then this one is like minus x1 y1 pi minus y1 pi minus y1 pi, something like that. So you can't mess up, so try to move a little bit. So similarly, I can make more equations here, right? So if I have another coordinate, I have like x2, y2, 1, 0, 0, 0, and so on and so forth. Now, right? So, and this is, the other side will be just equal to 0. So now I have another different equations. I have like something like ax is equal to 0 here. So it's similar to last time, but last time I have like something like ax is equal to y, right? But now I have ax equal to 0 here. So what should be the solution? So remember the last time, if I have ax equal to y, I just said like earlier I can do a pseudo inverse. So I have like x is equal to, let's say, y a transpose a inverse. So can I do that also? I see shaking head and also nodding. So which one? Oh, I don't know, honestly, like, how many of you guys are completely lost? Because I see many people are basically just doing their own thing. So I'm not sure it's because, okay, I appreciate your honesty. So, okay, maybe I go back a little bit here again. So what we were doing what we're trying again is like we're trying to map. So maybe I go back to one of the screens here. So say we are going to try to see if I have one of, yeah, I'm trying to do some stitching here. So to do this stitching, maybe like, if you remember, like, kind of like the lecture before that, like, we, at one call, maybe I have two images here. So one image is from one scene, or like from one point of view, the other image from another camera, another point of view there. And then we get some feature points there. And then we find the corresponding coordinate, maybe like, I think the beginning of the, have something, oh, okay, I don't actually. But say we have like some points here and then some points here. I know what's the corresponding points. I have like several of them. And then like I want to find the warping, like the corresponding warping from here to here. So basically I basically map each of the coordinate in this image to the coordinate in this image. And the mapping involved is I can use this so-called homogeneous coordinate, which is a homography. So we have the coordinate is going to be represent using the homogeneous coordinate. Let me go to here again. So this is the homogeneous coordinate. So if you have like any coordinate like this, I can just append an extra one there from a homogeneous coordinate. Or if you think of you have a homogeneous coordinate in general, like x, y, w, then the actual coordinate is like x over w and y over w. And you can think of like that is correspond to, if you have an x, y, w somewhere, like this scene here. So x, y, w is like some point like in the three-dimensional space. And then it's actually at that point you want to project to a virtual plane. There is like at w equal to 1 away from your camera. Now, yeah. 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 So, but we want to work on this coordinate because we want to like make everything in the framework of linear algebra. So if we were in this coordinate, we can represent all the transformation that we are interested in a matrix. Just is like you have a kind of like this is the original coordinate. If I want to do a first form of translation, then it will be just multiplied by this matrix I formed this one. So in the most general case, I will have this matrix here is kind of all arbitrary, kind of. But then if you just look at that, it looks like I have 9 degrees of freedom, but actually I only have 8 because like scaling doesn't matter. If you see here, I can scale something like it's just the same thing. Then now like back to the problem, like I want to try to see if I have like pair of coordinates, one image to another image, I have a lump of pairs there. I want to find the correct homography, the correct matrix here for the mapping. So then now get back to, yeah, basically get back to the story here then. So now I want to find this mapping here. So I have coordinates like this. Now then I will just make it general. I will let all 9 kind of like parameters or like coefficient in this matrix to be arbitrary. So it's just 9 unknowns here. And then like I have coordinates, yeah. So let's say I have like x1, y1 mapped to x1 pi, y1 pi here. So therefore like generally you see that like my x1 pi should satisfy this equation here, right? Because I have x1 pi here, you see, or I shouldn't say this x1 pi, maybe I write this as like x1 tilde, y1 tilde, x tilde, y tilde. Then x1 pi is actually equal to x1 tilde over, let's say this w1, say. W1 is like this guy here. So therefore, like you see, like this x1 pi is equal to this multiplied by this over this multiplied by this here. So therefore, I have this equation here. Oh, yes, yes, I hear like all, yes, let me call this like, yeah, remove this one. So, yeah, so then I have actually x pi is equal to x1, or like x tilde over w, something like that. Yeah. So it's a bit confusing, like my notation are not consistent. So similar, I have this equation here. So now I need to solve for this coefficient a, b, c, d, e, f, g, h, I, right? So then I said, like, okay, I can just move things around. That's very nice. I just multiply this to the other side, and I have like this guy x1 times a something minus this thing is equal to 0, right? And this also, like, this is equal to 0, something like that. Now then I can write it in a matrix form now. So it's like this x1, y1, 1, 0, 0, 0, 0, this guy here, multiplied by this a, b, c, d, e, f, g, h, I. This basically, this multiplied by this will correspond to this equation, right? Yeah. So everyone is okay with that? I heard when I'm in faculty meeting, I heard Joe Bob complain about like you guys didn't take the good like linear algebra. So I'm not sure it's Joe Bob or like, but anyway. So I'm thinking like maybe like you guys take the linear algebra, but like maybe didn't. Did you guys forced to take the linear algebra? Like, I think so. Like, did you already take that? Say in math. So how is that? Or like, is this too simple like for you, or like, do you get lost? Because I have no information, like kind of background knowledge of you guys, what you kind of taken or like not taken. Like,
where I came from, the course was combined with differential equations.
Yeah.
So it was kind of the basics of both.
Yeah.
Here it's a full.
But like this, like, do you feel like comfortable? Like just I write this and then this is equal to that. Like, do you need to a little bit time thinking or like? Okay, that's good. So I just want to make sure. So yeah. Then I this is like the first coordinates, first set of coordinates. I have like I can write these two lines of equations, right? So if I have another pair of coordinates, I say x1, x2, y2, x2, y2 map to, let's say, x2 pi, y2 pi. Then I have two more lines, something like x2, y2, 1, 0, 0, 0, x2 pi. Oh, sorry, that's a minus sign here. Minus y2 pi, and minus, okay. Minus y2 x2 pi minus x2, right? x2 pi. And something like that. Like I have 0, 0, 0, x2, y2, 1 minus x2, y2 pi minus y2, y2 pi. Oh, I think yeah. Minus y2 pi, right? Kind of like that. So then I said like I can if I have more equations. So how many equations? How many pairs I need? Be careful. Minimum pairs I need. Yes. 5, right? Because each pair I have like two equations. I have line unknowns here, so I list at least 5 pairs. So once I get 5 pairs, then potentially I can solve a solution. So basically I have some ax equal to 0, this kind of like problem now. So then my question is like, okay, I previously have similar set of linear equations like this. So I say that I can have a solution x equal to this guy here. Now can I do the same thing to solve for x here? Who say yes, who say no? So do you get my question? Like, okay. Again, like if you look at this, I can call this is equal to a, right? So if I have like 5 pairs of coordinates, I can have a. I call this x is equal to 0. Now I have like basically a problem. Ax equal to 0. I need to solve for x here. So I know that if like this is, if it's not equal to 0, maybe if it's is equal to some b there, then the solution will be like x is equal to A transpose A inverse A transpose B there.
Yeah.
Yeah. Now, but I know I have a problem like Ax equal to 0. So can I say like x is equal to this, so B is equal to 0? So no, yes. So, okay, why?
Because we're assuming that a solution is a trivial solution, but this is not always the case. We get the matrices, you can multiply two matrices that are non-zero, and you can end up with a zero matrix at the end. So by doing that, we're assuming no. If I'm multiplying two matrices and that result is zero, then one of them must be zero, and that's not correct.
Good. But my short answer is like if I do that, like my solution will be 0, right?
Yeah.
Yeah. So I'm definitely not interested in a solution is equal to 0, because like then basically I don't have anything. I'm saying that okay, my transform is just mapping everything to 0. So it's like I have a totally trivial solution there. So what should I do? I need to, here it's not clear, but I basically need to impose a constraint here. I need to force, let's say, this x. Say I can force anything, but I can say that I need to have this x have norm is equal to 1. So I just need to norm have something like I need to force this thing, like this whole parameters this cannot be 0. So maybe I can force this guy like the sum of square of this guy. Okay, you guys know what I mean, this norm here, right? So this norm here, when I write like this is just mean like x transpose x. If you look at this x transpose x is what? A, B, C, like up to I, and then multiply A up to I here. So therefore it's like A squared plus B squared and so on. Sum to I squared. So I want this to be 1, say.
Why?
No, I can put it anything, like I can put it C. As long as it's not 0, right? So I don't want it to be 0. So but let's say I just put it 1, so it doesn't matter. So I put an extra constraint. I want like this guy equal to 0, but I want to make sure like this is equal, let's say, equal to 1.
Okay.
So it's fair, right? So now okay, now what should I do? So I want this to be 0, so I can do something similar to what we have last time, right? We say, okay, we're trying to minimize, last time we were trying to minimize Ax minus B, the norm of that. Now instead, I basically have a problem of that, like I trying to minimize. Okay, I'm curious, like when you guys take the linear algebra, is that more abstract? Like, is there lots of like applications, or like how does it look like?
It really depends on the professor. Some professors like focus on the theory and they just like focus on the proof and stuff like that. Some people focus on the applications and they tell you, oh, we're using this to solve
Yeah.
like a physical problem that looks like that. It depends on who you took the class with and their background.
Really? Each year is different?
Yeah.
So, but all of you guys take from the math department, is that?
Yeah.
Okay. So, you know, there's a very famous professor in linear algebra in MIT, right? Gilbert or something, right? So if you need some kind of like revision, always go to like search for him like on YouTube, and his video is really good. So, but okay, so for this guy, okay, I say I'm trying to minimize this. So I change my problem a little bit. I try to kind of like solve this, minimize Ax here. So I want this to be 0, right? So I just try to minimize that, but I have a constraint that like x is equal to 1. So something like that. So you have many ways to solve that. Like the kind of standard way is using the Lagrange multiplier and so on. But I will just like give you an kind of like intuitive way. So I mean here, like when I write like this, also I also can rewrite this as a ax transpose multiplied by ax, right? So therefore, this is actually equal to x a transpose. Oh, sorry. X transpose a x, something like that. I want to minimize that such that x equal to 1. Now, okay, first of all, like you look at this, this is something, a form that is kind of like I always say, there's a name for that. What's the name for that? I am really bad at names. Some kind of quadratic forms, I don't know like what's the formal name for that. But you see that this is basically something like x transpose multiplied by, maybe I call it c multiplied by x right here. And what's more, like you see the central matrix here is it's actually it's symmetric, right? You agree with that, right? So it's symmetric because I have A transpose A. If I look at the transpose of that guy, what's that? Yes. You guys remember like A B transpose. What's A B transpose? Oh, nice. I like you. Thank you. So therefore, like yes, this is A transpose A. So this is symmetric. So C is symmetric. I'm not sure how many. Okay. This one you may not remember. So when you have a symmetric matrix, you can always find the set of eigenfactors that form the basis of the space there. For example, you have like C is like n by n. Then if this is a symmetric matrix, you always can find like a set of eigenfactors that span the n-dimensional space there. So this is a fact. So you can go back to the linear algebra textbook and you can look for that. So therefore, like I can say have the eigenvector say x1 up to. So I shouldn't use x1 again. It's confusing. So v1 up to vn. Let's say this is n by n, right? So these are the eigenvectors. And let's say I have the eigenvalues are sorted, so like ascendingly. So I have lambda 1 up to lambda n, and lambda 1 is less than lambda 2, and so on. Now note that like because this is a basis, right? So I can any x I can represent it by kind of a linear what's that called? Yeah. I can kind of form a linear combination of this like basis here, right? So let's say in arbitrary I have any x here, I can write it as let's say mu I times vi, I equal to 1 to n. So it's like any x I can represent like this, right? You agree with that, right? So because like this form the basis, and now. So and then like I say like I have the constraint like this, right? I have the constraint is equal to 1. Oh, by the way, when I say basis, they are orthogonal basis as well. So orthogonal means that like I have it's actually orthonormal. So I have like v1. If I look at the inner product of v1 and v2, this will be equal to 0. Let's say so any vi vj is equal to 0 if I not equal to j. And I have vi transpose vi is equal to 1, something like that. They are all orthonormal. So now if I represent x as this, now I can look at like what is the norm of x. Norm of x is equal to, I have an inner product, so I can write like this, I equal to 1 to n, mu I vi transpose, I equal to 1 to n mu I vi, right? Now what do I get here? Oh, okay, let's make it less confusing. I use different index. Like this one I, this I use j, I say.
Basically, we get the angle between the two
So okay, you guys have just taken linear algebra to be able to do that. That so what do I get like for this one? What?
So, are you not finding the linear combination and then dividing by the magnitude?
Remember we have the constraint here. So we say we have a constraint, this the norm of x equal to 1. So I can represent any x using this like basis here, right?
Yeah.
So I just want to see, okay, if I represent using this basis, of course this mu is kind of arbitrary, but I want to see like what kind of constraint I will have like on the mu's here. So to do that, I need to first know like, okay, what's x norm in terms of this representation, right? So x norm like is just equal to this thing, x transpose multiplied by x here. Okay? And how what's this? Like how do I proceed? So just work like an engineer, like mathematician is kind of magical, but engineer just do step by step, tiny steps. So I don't know what to do. Then I just like copy the whole thing again, right? So I can move this. I can move this like summation to the other side. This and her, right? So I can move summation, right? So I have I equal to 1 to n and j equal to 1 to n, right? So I have this like mu I vi. So by the way, like mu's are a scalar. Be careful. Like v. Okay, I maybe. Please don't be kind of confused here. These are eigenvectors, right? So v here are all like vectors, they're column vectors, but mu here is scalar. So just need a combination of them. So this is a scalar. I can put it out, right? This I can put it out here. I can mu I mu j. I put them together, right? And then have vi transpose vj, right? So now is that clear? Clear now? So we just have that, right? Yes. So we basically like all the bases are orthonormal. So therefore, like only when I equal to j is equal to 1, right? It's just equal to vi times vi. So the inner product is just equal to 1. All the rest will be just equal to 0, right? So essentially, like, this one is actually a delta product, right? Sorry. Yeah. It's a product like a conical delta or something like that. So it's actually a delta function, something like only when I equal to j that would be equal to 1. Other than that, it's just equal to 0. So I just copy that again. So right. But then this means that like I'm forcing I equal to j, right? I can erase one of the summation. So I will have like j is equal to I, and I erase some of the summation. I have like I equal to 1 and mu I times mu I or mu I square, right? So it's just sum of the mu square. So okay, then the constraint, if I want this equal to 1, just means that like the sum of the square of the coefficient is equal to 1. So it's like, again, you can think of this energy interpretation. It's just the energy equal to 1, right? So like it's like Fourier transform. If you have the square of the coefficient together, that's equal to the energy is equal to 1 there. Now then, like if I go back to here and do the same thing for this guy here. So I want to see like how about like x transpose A transpose. Okay, I erase this part here. So if I do the same thing, now I do the same thing for AX here. So I have like X transpose A transpose AX. Oh, this is C, right? Remember, like V1 and up to Vn are actually eigenvectors of like this C here. So I have X transpose. Now it's I rewrite this again. It's a summation mu I Vi transpose, right? I equal to 1 to n times A transpose, times C times summation j equal to 1 to n mu j vj transpose there. And, no transpose, I'm sorry. Right? So I have a transpose outside, but my transpose get inside, right? So now then all the V's are eigenvector of C, right? So what was C multiplied by this guy then? What was C multiplied by X here? C multiplied by this. This is a scale. This is a vector, right? So X is still a vector. I just represent it, right? No. C is the is equal to A transpose A. Yeah. So C again, I see is A transpose A, and all these three here are the eigenvectors of C. So okay, what's that? So okay, this operation is this is linear operation. C times this thing, so my C can get inside the summation, right? So it's if I have CA plus B is equal to CA plus CB, right? So this C I can get inside summation. And mu is a scalar, so I can pull mu out. So mu j C Vj, right? Yeah, and these are eigenvectors of C, right? So that means C Vj is equal to just lambda j Vj, right? Yeah, so I have this is actually mu j lambda j Vj. Of course, this is a scalar, right? So it's very similar as last time. Just I have now a lambda j here, right? So then actually, then of course I will basically just have I equal to 1 to m mu I square lambda I, right? Agree with that? Okay. If I just repeat the same thing like last time, so I have a delta function somehow, and then I just have mu. So one is that this is minimized, and I have a constraint. Remember, I have a constraint that sum of the mu square is equal to 1. And now I want to look for this to be minimized. So what's the option here? What should I pick mu's? Given that my lambdas are kind of given ascendingly. Yes, which one is 1? Yes, mu should be less than 1. It's not necessary. I can have one of them is 1 and then the rest is 0. Right? Yes.
Like the summation is not exceed 1.
Yes, sum of square is not exceed 1. So again, but I want to minimize this guy here. Right? I want to minimize this guy here. And I have the constraint I derived earlier that I say the norm is equal to 1. That's basically saying that the mu square is equal to 1 there. So what is the choice of mu that will minimize this guy and satisfy this constraint here? Yeah? What? Which one is 1? So okay, mu is a vector, right? Mu 1, mu 2, mu 3, mu 4. So you need to, let's say n is equal to 5. So I have mu 1, mu 2, mu 3, mu 4, mu 5, right? So what should I pick?
Only one of them to be
Which one?
Either the beginning or the end.
Okay, okay. Given that I just mentioned this, lambda 1 is less than lambda 2, less than lambda 3, less than lambda 4, lambda 5.
Last one is 1. The others is
I want to minimize, not
So the
maximize.
first one should be one. Because this is for the A vector that
Yes. If I first say first one is 1, I search 1, 0, 0, 0, then this value here will be just equal to lambda 1, right? Yeah, then it will be minimized, right? I cannot get smaller than that. So basically, I suggest what I should do is I should just pick mu1 equal to 1 and then the y equal to 0. And if I say mu1 equal to 1, then what is x? X is just equal to v1, right? So therefore, the solution is simply what? Simply is the minimum or the eigenvector of the corresponding minimum eigenvalues of like A transpose A. And okay, I guess and any question here? So basically, therefore, like what you can do is like you have some A matrix here. You can compute A transpose A, and then do a eigenvalue decomposition. Then you find the minimum eigenvector, the eigenvector of the corresponding minimum eigenvalue, and that will be your solution. And by the way, like that procedure can actually stabilize a little bit. Instead of doing eigenvalue decomposition, you can do single value decomposition. So by the way, like did they kind of mention this in when you take the linear algebra course, like single value decomposition? So Logan, did you just take that course? Like linear, did they mention single value decomposition?
Say it one more time.
This is a singular value decomposition.
Rings a bell. We have to do that something.
What?
Rings a bell. That's something.
Oh, okay. They mentioned that. Okay. So unlike eigenvalue decomposition, you have to a square matrix. So single value decomposition, the nice thing is that it can be any arbitrary matrix. So any arbitrary matrix, you have a single value decomposition. And basically, when you have a single value decomposition, it's something like you have A, you can decompose into some U times D times maybe V. So this is like diagonal. And U and V are kind of orthogonal. So like similar to what we have like when we have like eigenvalue decomposition that like have O, D, O transpose, something like that. And I'll probably put a transpose here. So these are kind of like orthogonal to one another. But so what I mean is that therefore I have U transpose U is equal to identity of V transpose V equal to identity, stuff like that. So what you can see if I use this single value decomposition and I consider A transpose A there, A transpose A, then it will be something like V transpose D transpose U times U transpose dV, something like that. And this is basically identity. And this is a diagonal matrix, just like the eigenvalue decomposition. This is a diagonal matrix. So therefore, it's just equal to D squared V transpose V. So what you get is like the single value decomposition of A is the same as doing an eigenvalue decomposition of A transpose A. And in that sense, that you can just simply do a single value decomposition of A and take the left side single eigenvector and the single vector that with the minimum single value, that will be your solution as well. And typically, this is more stable. And also, if you have the matrix, it's like very skilled. For example, in this case, may not be matter too much. Your A may not be too skilled. Like you may not get too many pairs of points there. But anyway, like this is one option. So okay, anyway, like I go back to the slides. I guess I cover most of the stuff. So this is what I mentioned there. Square. So we mentioned that if we solve for homography, then we have like something like that. So instead we should do a kind of solve for this, that essentially will just give us the that's the eigenvector of A transpose A with the smallest eigenvalue there. And let's see, I have like 10 minutes. I don't know whether like I should go very quickly on this or like leave it next time. Maybe I mentioned a little bit about like project presentation now. Then next time I guess I will have. I don't want to watch because so oh, and of course, presentation is coming up pretty soon. I don't know when was that. I forgot. I guess like this I have. Oh, spring break. Is that like this week? I forgot. So so in about 2 weeks, right? The presentation. Right? So just like some okay. Something that most importantly. For the rest of you guys who are not presenting, it doesn't mean that you don't need to come or you don't need to do anything. So I really need your input, like for the rest of you guys. So I'm not supposed to be the one to judge, and so I will let you guys to judge the presentation somehow. So you guys, I will put up kind of like a very short assignment. So it's a questionnaire in on Canvas. So you just fill in like, most importantly, fill in some score, but more importantly, like I want you guys like each time just put up some constructive comments. Just like a line is okay. Like what is the strength and weaknesses? That's really helpful. That's it. Actually, typically what I do is I will gather all this and send it back to the presenter, and it's really helpful to them, to them. So okay, you will be kind of like, of course, the task is not, I don't ask you guys to do it for free, so that will contribute to some credit as well. But not extra credit, it's mandatory. So, but it's kind of tiny, but for that part, I want to emphasize again, I won't allow late submission for that guy, because I think it doesn't make sense like when you have a presentation now and then like 2 weeks later on you submit a kind of like what's the comment for that, and then I'm not sure how I should kind of like evaluate that comment. So then I would just give you a rather short time frame, like but reasonable, I guess like 36 hours. Like, by the end of the next day, midnight, I would want you guys to put in that evaluation. And this time, as I mentioned, because I really don't want you guys to have late submission, so I won't be accepted. So I will just put it ahead, because each year someone will ask me like, I have some certain reason that I cannot get in, so therefore like I cannot blah blah blah. But I always tell them like, don't worry about that. It's just 1%, or like I don't know how much it's less than like a very tiny percentage. It's like 1 point there. So if you miss a couple, it shouldn't affect your grade. So unless you miss everything, then will contribute about like 1 homework assignment. So you don't want to miss all of them. Like maybe you miss some, is okay. So okay, this is already project proposal. So and for the presenter, so this is just a kind of general guideline, but as I said, like depends on the problem. Right? If your problem is pretty um, non-conventional, you may need more time to introduce the problem that no one even aware that it exists. But then I still would like you to spend a little bit time on the solution. So even if you may not really have really lots of time on that, but it would be up to a certain point of abstraction. If you don't have like so much time, then see if you are able to abstract the idea quickly. So instead of go for all the math, like if you have more time, maybe you can go for some of the math. It's not necessary though. And if you don't have time, you just go for high level, right? So you have this component. Maybe it's this, you have this, first do this coin detector, and then this, you have this feature, and this, like combine this, and blah, 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 and solve this equation, and so on. You may not even have to know exactly how you solve it. Maybe you know that, okay, to solve this, you need to use this. Maybe you have a pointer, even that pointer will be useful, right? Maybe later on, when we have time, we can dig into that. And for the audience, if they are interested, they know where they can look into it. So think of like what the audience will gain. Like, so hopefully it's like everyone will gain something. That's the idea. So and as I said, like audience, I will put up the task, and you guys will just submit some comments there. And that's in general for the final project. I will ask you guys to put in a proposal as well, like early April. So just want to make sure you guys didn't start like until the very last day, and so I guess by that time you should kind of figure out like what kind of project you want to work on, and if you want to make a group project, that's fine. If you want to do it alone, it's fine as well. And I think like I have a pretty original grading rule in terms of teamwork. I don't know about the other classes. Maybe some of them like are more biased into teamwork. Actually, I'm kind of not exactly counter that, but I'm not sure it makes sense that if you have like 4 team members to work on something, that not sure like who is working on what or something like that. So I actually have a small, I don't know whether I put it here. Yeah, I have a small bias in terms of like the group getting too large. Basically, I have a deduction in the percentage if you are group member more than 2 starting from, but the kind of the penalty is like kind of exponentially going up. So like it's kind of minor if you have only 3 members, it'll be like 5%. But if you have like 7 members, I don't think it makes sense at all. So it will be like 80% deduction. I don't know if it makes sense. I think like I don't know like I'm not sure like other professors agree with that. But I think like if in the workplace, I don't want to hire 8 guys to do one tiny project. It doesn't make sense. So that's the idea there. In terms of the proposal, okay. Yeah, I guess I would just mention a proposal first because that would be due first. So you should most importantly define your problem, like what you really want to tackle. Maybe you can put in some approaches already, but you may not be kind of like constrained at that point, and maybe afterward you study more, you find out, okay, actually it was not really a good idea, you can change it, it doesn't matter. Anyway, like the idea of the proposal again, like I just want to push you guys to start early, so it will grade very loosely, don't worry about that. Like it's like basically as long as you submit typical, just give everyone like all the marks there, all the points there, but I just want to push you guys like to do it earlier and really think it through. So I guess that's about it. And for this, the final submission will be like, I guess it's around I think it's May 7, something like that. I think. So you're required to submit a kind of like a report submission. So it's a written report, and the written report, any kind of format is okay. So as long as you have like the components, it makes sense. Like talk about what's the problem and what did you actually do? Something like what approaches you tried and like how does it work, or like how it doesn't work. Even how it doesn't work, it is okay. And it's kind of gray loosely like this one. We look at presentation, tackle, and that kind of stuff. And and optionally, like if you want to earn some extra credit, you can submit a kind of screencast as well. So, but that one is not mandatory. I forgot how much okay. So probably like 20% of that or something like that. So. Okay, so in terms of expectation, this is like what I'm expecting, like approximately the grade, like this is like, for example, like if your work is kind of like acceptable to a kind of a national conference and so on, if you're a graduate, you will probably get all the mark there. So it's not saying that, okay, I'm not to be confused, I didn't mean that like by that time you should have already submitted to a conference. It's just like, if look at that, it feel like it's like in that standard, then yeah. So if like undergrad side is a little bit, the requirement is a little bit less. So you have this university level conference like once a while. Like if you meet that tough standard, that you will get all the marks as well. So if you just submit and basically it's like really unbearable, it's still you will get 1/3 of the marks. But probably it's really bad. Like don't do that. Like you may fail this class. So, yeah. What?
What are the differences? Like how are you gonna feel that this is actually like
I'm sorry. It's like based on my years of experience. It's hard to say. Like if you have chance to be a reviewer, like it's then I would say like it's actually the difference is not that much. I would say, so I won't judge you guys based on novelty really, because like that is like it's kind of difficult. It's mostly based on the
Basically just asking for like high quality writing that sort of know what you're doing. Or is it like innovation?
It would be like you include all the necessary information for the readers. If you think of your readers, you're reading that, like you have lots of questions coming to mind, right? So does it answer all your questions? Kind of. So that would be like the best scenario would be like that, right? If you do something like that, I'm for sure that you will get up to the national level, like conference and so on. So basically, it's full. Like people look at that, like all the questions are basically answered. Like, and of course, this can be. It depends on how eventually, like the outcome of like so. But even though the outcome is not as great as you're supposed to be, you can still conjecture, right? So people still can have like lots of questions in their mind. Okay, you did that, and it doesn't work out as good. Like, and then maybe you can give out some reason, right? And you can like rationale over that, and yeah. And if your answer is convincing, then I guess people will appreciate that also. So.
You said there was or wasn't a presentation attached to this project?
Oh, it's optional. So if you want to get some extra credit, just by the time you think, oh, you want to get some extra.
Presentation and rubric?
The presentation is the same. So the rubric is basically the same. So you want to. Of the difference is like, of course, it will be basically the same thing. So, if you do a presentation, just like a similar manner. And also like, if a presentation, that would be like, okay, if you go to a conference presentation, honestly, this is like pretty hard also. Like, your conference presentation is really bad sometimes, occasionally. So there is, but for that one, if you really that part honestly I will make it like kind of proportional to the other part. So don't expect if you have this written report is really bad and you have the presentation that you will have grade kind of like proportional, not proportional to the written report. That is not typical. That won't happen. Like, yeah. So you can, but you will still get the extra credit. Something like if you have like, for example, you get 70% from the written report, and you do the extra credit there. Then you also get 70% of that, whatever extra credit also, kind of like that. Yeah. So okay, I'll talk to you guys on Thursday then.